Good evening, everyone. This is Aishwarya Mantha with Fluor. I am the Global Technology Development Lead here with Construction and Fabrication. And what today's session, our information session 2, will be about the hydraulic component of the design challenge. It's 4:01 p.m. We'll wait for a few more minutes before we start this session. I'm going to give it a couple of more minutes before we start the session.
Okay. On your laptop.
All right. I think we should get started. So the main purpose of this, our second info session, is explaining the hydraulic component of the design challenge. David Bogle, who is our Fluor pipeline functional process leader, which also translates to him being an authority on pipeline design, will be talking about the hydraulics. The key message here is that we've made some revisions to the original narrative. So he'll be going over what those changes are, followed by a demo of how to run the software that we have recommended. And then, so that's going to be for 30 minutes. Then we'll open up the stage for question and answers. And if we have students from both College of Engineering and College of Technology, perhaps we can get together. We'll save some time, either for this session or the last 10 minutes of this session, depending on how much time we have left. You can interact to see whether you would like to collaborate on how you want to pursue this challenge. So in this meeting, we also have Ron May. He's the subject matter expert on all everything to do with civil design and excavation and foundation. So wherever required, he will also chime in to provide his expertise and thoughts specific to the revisions that have been made. So without further ado, before that, I want to make sure that everyone can see the screen. So if you can, on the side, on the chat bar, respond by saying that you're able to see the screen. In fact, those who cannot, please type it up. I would assume that the ones who have not responded can actually hear me and also see the screen. So without further ado, David Bogle, please go ahead.
All right, thank you. So appreciate everyone attending the information session number 2. The first one covered the general requirements of the overall challenge, which included describing the purpose and mechanical design of pipeline, hydraulics a bit, and civil design requirements, and how it all translates into our construction-driven execution philosophy. And so this one's focused on the hydraulic analysis, and I will be giving a demo of the software that you'll be using to run the hydraulic analysis, as well as identifying how we determine selection. Before we start into talking through the slide as well as the document, I'd like to tell a little bit of a story around some of my own experiences. So Fluor, we have several things to take very seriously, safety being one of them. So with quality, we conduct audits within our own projects where, in my particular group, I probably have about 500 questions or so that we go through a process of auditing. And through those 500 questions, every single one is very important that we cover in our design correctly. And through that verification of asking those questions, it's validated that we have done our work in accordance with the plan. One of those questions just so happens to be whether or not we have an approved software list. And that approved software list is our listing of all of the software that we use, as well as the versions that we use. And I've been caught multiple times in not having either the assigned and agreed upon software list or using the wrong version. And I apparently haven't learned my lesson quite yet, because that's what we ran into in this situation. So as I was preparing all the design challenge, the version that we utilize here at Fluor and our approved software was not the same one that was distributed to the rest of the students. So hopefully you can take away from that something better than what I have done in the past, and be able to execute your work better than I did. But the good news is the way that the software works is, well, first going to be able to conduct this. There's only a couple of modifications that need to happen, and I've documented this in an updated design challenge, which will be published to you and available on the website for you to download. There was going to be an amendment already to identify how the pumps are identified. So you did already anticipate having additional information, and this new version, Rev 1, will also document the modifications that you need to do to be able to use your student version of the AFT Fathom license. All right. So I did want to reiterate there is something in this for you. So we're looking at distributing $3,000 amongst the top 3 teams. So there's some financial rewards in this for you, as well as a certificate to go on your resume. I do include the design challenge requirements where you can get that revision 1, as well as the cost estimating spreadsheet and some other templates to help you along your way. And also note that the software that you'll be downloading, the link is also provided there, where you use your U of H email address to be able to get that license. I wanted to quickly go and just show you what your model would end up looking like. Of course, it doesn't have to look like this by any means, but I like to build it more in line with how the elevation is laid out. That helps me visualize and get an idea of where each of the junctions are and how the resulting pressures are going to be displayed later. But effectively, this is how your model will be built, where you have pressure inlet and a pressure outlet at the end. The way that the pipe is pieced together will be with what's called a branch connection. That's where each of the gray circles are. And your goal will be to figure out where to put the pump. And it's not just driven by hydraulics, but you'll also need to consider the excavation requirements and other related soil design criteria to make the best selection based on the resulting cost of this line. And I'll go into more detail, and of course in the demo, talk a lot more about that. So generally, here are some of the input parameters for your hydraulic analysis, which will include our flow rate, our inlet and outlet pressure. We'll be looking at maintaining a certain velocity in the pipeline. I'll talk a little bit more about that too. And then just setting up the process conditions for the fluid that's in the line. And along with, as I mentioned, the adjustments and the versions of the software will only allow for 12 segments of pipeline. So these are the junctions. So you'll see in 13 rather than the 12. So that these are the beginning and middle points of all the lines. And this is how you will build the data into the overall model for what we call the branch, or those gray circles. So I'll be reflecting back on this table as I go through the process of building the model.
David? Sorry to interrupt. Could you go back to the previous slide, please? And the one before. Yes. So students, kindly note that the indication in the red font means the change from the previous version to this version. And this is something that's consistent in the design narrative as well. For example, I think in the original version, it was gallons per hour, right, David? And
That's correct.
That's okay. And now we fixed that to show it gallons per minute. So whatever you see in red indicates a change from the previous version. And the narrative that we are going to be uploading actually will be in the same form, wherein everything in red you will is a change from the previous version. Sorry to interrupt, David. I thought we needed to clarify that. Thanks.
No, I appreciate that. And as I go through the rest of the actual document, you'll see more of the red text, and I'll go into the design challenge to show that as well. But what you'll be looking for is for the performance of the pump, we're going to look at two aspects of pump acceptance, and it's the net positive suction head available must be greater than what we're identifying in our pump table, and what this means is we want a certain pressure on the upstream side of the pump so as not to create a vacuum or cavitation as the pump is operating. So each one of the pumps in the table, and I'll show you that, will have a different net positive suction head available, and in the software itself it'll be referenced as NPSHA, and I'll show you where that's located as well. The second criteria is simply the horsepower of the pump selected must be greater than what the hydraulic analysis has identified for the system. There is significantly more to consider for pump stations. However, our focus on this particular challenge is to look at the construction-driven execution, and as you move that pump around, we didn't want to add too much criteria or go into too much engineering design that it would not allow other disciplines or in other groups to be able to participate. So with these two sets of criteria, it allows us to build the model and have results that we can compare one to another and allow us to come to a solution. So there will be variations in your design, and these two items will allow for that to happen fairly easily. Okay, so before we run off to the live demo, I'm going to just run through some of our changes in the new design challenge. So this is Rev 1, and it should be up on your screen now. Okay. And Aish, can you just verify that you see the design challenge now?
Yes, David, I can see it.
Okay, thank you. Looked like I was sharing two things. All right, it should say Rev 1, and you should be able to pull it down from the website fairly shortly. We're looking at getting that published here now. So again, because of the differences that I was initially building the screenshots and the descriptions for Fathom, there are some adjustments, and the majority of them that are documented here are related to that adjustment. And it's how you build elevations into the model, as well as how many pipe segments that we can use. And the student version is a little, I feel that it's a little more user-friendly, and the ability to make variations is easier. So this should be a positive move for us, resultingly from this. So all throughout the document, I've added table references numbers and titles to help navigate through that and help you with addressing any questions as well. We did add clarification around the cut calculations for the slopes, as well as how you approach it from a ZBE, or zero-based execution perspective. We added in an additional requirement in and around sizing a concrete foundation. So, just as we start executing a project, every once in a while there will be a little modification from our clients, and so this is definitely a real-world type of experience for you. The sections around soils reduced to 12, and that's associated with how many pipe segments we have. So the soils all actually stay the same along the route as we currently had. The only adjustment would be some slight modifications to some of the slopes, and you'll be able to see that once you start going into it. We did add a section that further describes ZBE requirements and around modularization to help you with your design narrative and to really focus in on the differences between the two. So this is or a couple of the major concepts that we wanted for you to learn and get some experience around as well. The next, just about all the other items are related to just showing the new screenshots associated with the student version. The other one that Aish mentioned before was the flow rate, and initially as it was published it showed gallons per hour. It is actually gallons per minute, and that's the default in Fathom, so just make sure that you don't change that unit of measurement. Make sure it is gallons per minute. There were a couple of criteria that were added in to assist you, or we removed one and then added in another to assist you with sizing of the line when it comes to our zero-based execution approach. And then again, it's just updating the model shots. So just kind of quickly show you what they look like so you know what to look for. Again, everything that's in red is just additions to what was already in the original design challenge. Like I mentioned, adding in table references so that you can easily reference back. And again, more definition around how we handle the cut and fill and the zero-based execution approach to cut and fill. So you'll also see the red triangles, which should pop out if the red text doesn't do it itself. This was one of the bigger changes, mainly because we have to have the 12 different sections. So there will be differences in stationing, so it's not all 10,000 feet apiece. There's some that have 20, some that have 30,000 feet, and that's so we could get 12 segments of pipe in the model and not exceed that number. But the associated soil types are all the same based on the same stationing. As mentioned before, I did add in some more clarifications around the ZBE and modularization that identify our initial decision and what you will submit as part of your proposal, but then also the change to be evaluated as part of the ZBE exercise. So initially, as an example, the pump hours of operation for the initial design is the 8 hours per day, and that's the flow rate that was associated with that. What the change is they made a decision of it doesn't make sense just to operate this 8 hours a day. Why not operate it 24 hours a day? The reduction will be into the overall flow rate, so you'll still have the same volume per day, but you'll have to modify the flow rate based on that volume. And what that will do is allow you to change your pipe diameter. So we want that to be all documented in the narrative under ZBE. And the others are other items that we want you to address as well. So take your time to go through each one of those, as that will be part of your overall submittal. This remains the same up until we get into our the appendix, which covers all of the hydraulic and pump selection instructions. The entire next section, I'll go back to the actual demo, but this will be your initial interface with the AFT Fathom program. And again, I have the model that's a model shot that's put in here that I produced a little bit earlier, and each of the following instructions in here will show what all of your icons that you'll be using, what they are, describing a little around each of the icons, all of our process conditions, the elevation profile that you'll input, and then it goes into all the windows. So I won't continue past this, but the design challenge instruction does have all these window shots that describe what you will change. But I'm going to go back to here, and I'm actually going to use this because I'm going to refer back to the table as we build it, and go into the AFT software. So give me a moment as I move to the software. Alright, so it should be pulling up the program now. Alright, and I will continue with the demo. If anyone has any issues in seeing what's on the screen showing AFT Fathom student, just let me know and I'll make a correction. Alright, so this is your first interface with the software, and it's pretty straightforward software system, and it doesn't take a whole lot of time. So I'm going to go through the entire model and show you an example and how you can make your variations in your design. So the things that we want to do to make your life easier is to select the US only unit system. So that'll give us our PSI as well as heat. And then the other part that will globally change the process conditions for a fluid is around set the work fluid, and I'm going to just set it at a nice room temperature of 72 degrees, and then simply start building your model. So we'll just say yes to the next and OK for the next window. Alright, so in the previous, the design challenge, we had the 4 icons that were identified. We had the assigned pressure, our pipe, the branch connection, and then the pump. So those are the 4 icons that we'll be using. So our design challenge is taking water from an existing pipeline and following the terrain where the terrain changes along the route, and it will end up going up an elevation change that will end up requiring a pump station. So we do have an initial pressure requirement. So you change your initial input pressure by double-clicking on that, on the assigned pressure icon. And for this particular one, we had the 100 PSIG, and these are starting with PSIA, so just make the adjustment to PSIG. And if you go back to the table that contains the elevations, your starting point is at 2,000 feet. So So those are the only two input data for your junction 1, which is your assigned pressures. So then we have the pipe. So it's just clicking on the pipe segment, adding the segment in, and then also you'll have your branch connection. So that's simply how you build it. So since we will have 12 segments of pipe, we will have 12 of the P1, so it would be P1 through P12, and then you'll have junctions, or the J's, up to 13, which include the very final one. So I'm going to go through the process of just building each of these segments, and like I said, I like to show it as the elevation profile shows, and it helps me visualize what's going on. And it does not have to be perfect by any means, because it's just a representation of your pipe, and it's the most important part is just to have the pipe segments in there, your pressure input, your pressure output. Okay, I'll have one more of those. And then the final will not be a branch, it will be an actual other assigned pressure. That assigned pressure is what we're targeting to have the 50 psi to be able to place the water into the reservoir. If your assigned, or if your actual pressure ends up being lower than that, your model will end up showing that there's an error. And I'm actually going to run it after I put this in, because we're here already. The elevation at this location is 4,000, so you know that there's the starting point's 2,000 feet. It drops in elevation down to 0 down here, and then has to do a rise of 4,000. So there's obviously some elevation head pressure that's going to be working against you. The designated delivery pressure is 50 psig, so I'll make that adjustment as well. So it's just those two input data there. Alright, so for each segment of pipe, the software is fairly friendly, where I can input some preliminary data or some data in here that it will also continue on down the line. Alright, so this is how we define the pipe. Under pipe material, and we will select the steel ANSI. What that allows us to do is get into our standard units for the imperial units, and we've identified the 30-inch line as our starting point for the diameter. And we're gonna always use standard wall thickness, which translates to 0.375-inch wall thickness. So this is the inner diameter, so it's the 30 minus the 29.25 divided by 2. That's your 0.375. For all our purposes, we'll keep this wall thickness for the hydraulic analysis. However, it's extremely important, and a huge part of this challenge is to do calculations for wall thickness and come up with that exact value to be part of your mill order, or what you end up purchasing. So while we do hydraulic analysis around this, it will give us what we're intending out of it, which is our pump requirements. You will calculate your own wall thickness. Alright, so I will also reflect back to the table 7 in the design challenge for the links along the line. So that first P1 segment will be 10,000 feet. So I've included distance. We have all the definitions around the pipe, just diameter and wall thickness. There is a lot more information that you can manipulate within this table, but we want to keep as much of the default settings as possible. Like, for example, the roughness factor, depending on the type of pipe that you order, or if you're evaluating corroded pipe, this roughness factor changes, and how that affects your hydraulic analysis is you lose pressure. The higher the roughness, the more pressure loss along the line. And when we run the analysis and see the pressure curve, you'll be able to see what some of those losses are based on this roughness factor here. Okay. All right. So as we continue down in building the model, again, like I said, the software is nice and it copies over some of the previous entered data. So it's just a matter of me entering in the information in accordance with Table 7. Here we go, 10,000, 10,000, 10,000 again. And then we have 20,000. And once you've built this model one time, then you can save a copy, and I'll do that as well. $20,000. And I'm just looking at Table 7 while I'm building this. And the next two are 10,000. Okay. And the next one is 30,000. And almost there. Another 20,000 feet. So that should equate to the total of 200,000 feet along the route. Okay. So all we put in there was distances. What we haven't done, and that was the difference between previous version and now, is how do we put in elevations. So junction 1 with the assigned pressure has already defined the elevation at 2,000. Okay. However, the elevations along this line, it's just going to copy for now, but we'll need to input it in accordance with the information in Table 7 as well. This one happened to be right. This one goes down to 0 feet. That one's 0, so it's a copy of previous. And now we start going back uphill at 500, at 800, at 1,200, Okay, so that got everything in there. Okay, so now that we have everything entered in. You can also go to another table that I clicked on under model data just to take a look at all of the entries. And we should be in good shape. I'm just taking a quick peek through this. Inlet's 2,000, outlet 4, inlet pressure 100, outlet is 50. So with all that said, we should be able to run the analysis, and if there are errors, I'll say this as our base case, and you may have noticed I didn't put a pump in, so I did that on purpose too. And it's for purposes of seeing, you know, how errors are displayed, and as well, if you make an error during the process of creating your model, there will be a table that pops up that you can quickly click on the red item, and it will take you to how to change that input data. But if we look at the graph of results, the table that pops up here to the right is what we'll be looking for, and we want to look at the profile, the pressure profile. We'll select all for all the pipes, and I like my units in PSIG, and as we tried to generate it, it looks kind of crazy, right?
David, can you please explain why it's crazy?
Okay, and I think that what I was actually looking for was a little error saying that the pressure was below the volumetric, and that's primarily the reason why. But what I wanted, what we need to actually do is to build a pump into this, and one second, cancel out of that, and so the pump icon. Because I'm making the changes, it's going to ask me to delete, or it's going to delete the previous data. What I want to do is insert a pump just in a location along the length of the line. I'm just going to pick the J4 location. So I try to look at what the elevation was, because you'll see them as you go up each of the junctions. This one's at 0. Because that'll be an input into the pump designation as well. So I'll delete that branch and then drop in the pump, make sure that it's connected correctly. And then we go into defining the inputs for the pump, and this is also very simple. What we're going to be doing is, for the pump model, we're going to look at the volumetric flow rate fixed. That's why. Is to include a flow rate in here as the 11,111 gallons per minute, and with the inlet elevation of 0 feet. So we have to make sure we know what the inlet elevation is, get in your flow rate, and hit OK. Okay. All right, and we can run the analysis here as well and look at our graph results and go to our profile, select all. Okay. So what this chart is doing, and this will be a big part of what you focus on for your results and around calculating wall thickness. So as we see, we started with 100 PSIG, and there's a slight drop off because of the hydraulic losses for that first 10,000 feet. And if you remember, the elevation drops from 2,000 feet down to 0. So as it goes down the hill, your pressure increases. So just that 2,000 feet, we rise about up to 900, 950 psi. And before we even get to the pump, there's a little drop in pressure, and then we located the pump at this location at that 30,000 foot mark. The vertical line is what your pump is doing so that it can reach a 50 psi pressure at the end of the line. So once it increases the pressure from the 900 and some psi to the 1900 psi, all this drop in the pressure is due to the line going up the hill. So at your lowest point, just downstream of the pump, that's your highest pressure. As you go up elevation, the pressure drops, and it finally arrives at the solution that you need this much pump pressure to be able to achieve the 50 psi based on locating that pump at that particular location. So what you will be tasked with is deciding if this location is good enough for your solution and selecting a pump based on the performance, as I'll show you in a second, or do you start moving that pump at different junctions along the way. So each of the branch connections or the J numbers are opportunities for you to place that pump, and you can run the analysis to see how the pressure graph starts to represent the pressure. Note that if you have pipe that is at 1900 psi, that your design of that wall thickness of that particular piece of pipe needs to be able to contain that 1900 psi. That's why this pressure chart becomes very important. And in the design challenge, we've identified for you to be able to have 3 different wall thicknesses of pipe. If we tried to design this entire route based on the 1900 psi, then there's a lot of wasted steel. So your task will be to figure out how much pipe you want to order at a certain pressure rating. As you can see, there will be some pipe that can be at a lower pressure rating, so that's for you to determine, and it will be a large amount of the variety between each of the teams. All right, for the actual selection of the pumps themselves, there's this tab up above, so you'll have under output, it'll start under general, but if you move to pump summary, you will see two of those main items that we're looking at. As mentioned before, it's the net positive suction head available, this number in feet. We've identified several pumps that have the minimum requirements for net positive suction head available, and then also a designation for the horsepower for each of those pumps. Now, typically, a pump station would consist of multiple pumps as well as redundancy of pumps in the case where something goes wrong, is shut down, or doing some maintenance. However, we're just going to focus in and looking at this as an overall pump station and not go into the level of detail as I just mentioned. So we're focused on the overall horsepower, meeting the minimum requirements, as well as the net positive suction head. Another item to pay attention to is the velocity in the line. So with your volumetric flow rate of 11,111, that for the 30-inch line, it produces a velocity in the line of 5.305 feet per second. This is probably about right. We don't want the velocity going over 8 feet per second. what tends to happen in the water lines or any liquid lines is that there will be erosion that will tend to occur of just the water and any kind of debris in the line that will start eroding the pipe. So we want to keep a velocity below 8 feet per second, but also higher than 2 feet per second. So as you start to, so we've already set the diameter of the line at 30 inch, but when we start looking at the zero-based execution, the velocity for the minimum maximum should be considered. So pay attention to this during ZBE. All right, so I'm going to now. That was the model, and like I said, it's pretty easy to use. Modifying it and keeping record of it, so you can save this version as the 30,000 case, and then let's just say save as a. Let's do another one just real quick for 40,000, and as I mentioned before, it's good to take a peek at the elevation of 500. So I just delete this, add in a new pump, make sure we add in the junction, check the elevations at 0, okay, and 500, volumetric flow rate, 11111, okay. And that's as simple as making the modification, run your model, check the results, look at the profile. I did BS. And that's as quickly as you can make modifications to the model to be able to see what variations you have in looking at positioning your pump. And as you can see, you went from the high of the 1900 psi down to around 1725 or so. So that's as easy as it is to make those kind of modifications. All right, so I will go to our design challenge narrative. To show a couple of the tables that we included related to the pump selection. So a lot of these tables you'll see and be familiar with as I ran through the model. But here's the pump selection criteria. So we have pump A, B, C, D, E, and F, and the criteria is based on the net positive suction head available is in feet, and then the horsepower. So between those two sets of criteria, you should be able to identify a pump. Now, you can select the pump, but what does that mean? How does that impact your construction? Because, again, this is a construction-driven execution, which all translates to cost. So each of these pumps have a certain weight, and the P is the weight that you'll use to size the foundations. And we do show a difference between stick-built and modularization, which will tie into the ZBE approach. Also, there are differences in the dimensions of the what we're calling the pump station, or modularized, or even our stick-built pump station. The dimensions that are shown here also drives the sizing of the foundation. So between the weight P and the dimensions of the overall pump to be taken into consideration, that will determine some of your design aspects for the foundation. And the info session number 3 tomorrow will go into detail around foundation design. The other aspect is, again, all leading to dollars. So we have a dollar figure for each of the pumps, A, B, C, D, E, and F. that have some variations in them, and specifically around stick build versus modularization. And we also want to bring it to your attention that the numbers that are in here is specifically for this challenge, and to really drive home to be able to distinguish between your selections of the pumps, just so that we're capturing this overall concept. So they are arbitrary, and so don't take them as if this is the only that they all are weigh such differences or have such differences in dollars. In reality, they're probably a lot closer together with each other. But for this challenge, we want you to use this table for your design aspects, as well as adding cost into your cost estimating spreadsheet. So with each of the dollars associated with the pump that you pick, the cost estimating spreadsheet is, I'll show you how you'll just add that into, add it into your, and add it, I think I was sharing it, now I'm not. I will get there one more second. Okay. This is the cost estimating spreadsheet, and the way that you'll include your cost for the pumps is simply as you select A, B, C, D, E, or F pump. For the original design, they'll only have one quantity of each of the pumps, and then you'll add in whatever the cost of that pump ended up being. So that is as simple as it is to do that. So if you end up selecting pump A, you'll put quantity 1 and the actual dollars. During the ZBE exercise, we say that picking just one pump station is no longer a requirement. You can actually pick multiple pump stations, so that's why we left the input for team entry to be a part of your responsibility. So if you end up picking 100 pump stations, which I don't recommend, but that is your option to do that. So that's how you input the pump information into the cost estimating spreadsheet. So that concludes the demonstration of a model and what we're trying to achieve through the use of the software. Like I said, it's pretty straightforward. It's just a matter of getting the input built into the software, and then making the variations as your team seems fit to do so. And as I kind of wrap this up, and we can go to some of the questions, I wanted to just point out to some of our important dates. The portal for submission of your proposals will close on October 18th. And once we have those in hand, we'll go through our own evaluation process, and then be announcing or inviting the teams in the top to give their presentations to our Fluor team here over in our Sugar Land campus between October 28th and November 1st, with November 1st being the announcement for the winner. Okay. If there is anything that our Fluor team would like to bring up before we go to questions, let's do that now.
Ron, do you have anything to add to this?
Not in particular. We are going to be talking tomorrow in session 3 at 4 o'clock about the excavation and foundation design aspects of the design challenge. So you'll want to participate in that to get some more information.
Yeah. if you don't want to ask the questions now, my email address is at the bottom of the presentation, and I highly recommend for you to reach out to me. I try to be as responsive and as clear and concise as possible, but I do want to make myself available for any of your questions, and please email me. So if there's anything around the design challenge, focus those questions on me. I know the reason why I found out about the differences in our versions was our software, that the company AFT did come to me and make that announcement. So I appreciated the initiative of the student to reach out to AFT to find answers why there was some differences. But also keep me in the loop too, so I know to make those kind of adjustments. But again, if there's any questions, you can email me, and we can certainly open it up to questions to the team now too.
I'll unmute everyone, or whoever has a question, kindly unmute your mic so we are able to hear your question. So right now we'd like to open up the forum for questions. I think, David, I feel that we'll have more questions once they start working on setting up the model, and, perhaps then they'll have questions. Right now it's a lot of information in one go. I do have a question here being asked on the chat. This is from Mushtaba Musafir Ali Memon. I'm sorry if I didn't pronounce your name correctly. And his question is, hi, I'm at the library, so I cannot speak using the microphone, but I want to ask about team building. Okay, please go ahead and type up your message. What specific question do you have on team building? If you are able to type your message, that would be good. And as you're typing it up, perhaps I can say that while it is highly recommended to have a cross-disciplinary team with someone from construction management and some from engineering, it is recommended, but it's not mandatory. So if you run into any, and the way we have the narrative written up, it's very detailed. It's running some, formulas and calculations on Excel. But gaining that, if you're an engineer, you can leverage, you can close the gap by seeking out, perhaps even reaching out to some of the professors from College of Technology and Construction Management, or you can ask us. We should be able to answer that question for you as well. Again, cross-functional teams, cross-discipline teams are highly recommended and encouraged, but if that's something that poses a logistic concern, it's all right. So that would be my answer to this subject on team building. Is that what you wanted to get clarified? I think everyone can see on the side if they look at the chatting window. So if you're not able to ask a question based on where you are sitting, you can also type up your question. So his question is, when are we going to meet with engineers from other engineering disciplines? Also, these information sessions, the way we are holding, we are arranging for one room for all the people to dial into the WebEx from that one room, and that's opened up to both Fluor. That's opened up to students from College of Technology as well as College of Engineering. And that would be an ideal place for you to interact with students from other disciplines there. So we highly encourage you to attend this information session from the U of H campus if possible, perhaps tomorrow if your schedule permits. Then we would highly encourage you to take it in person from one of the rooms. And I believe Jennifer Knobloch from College of Technology and Charlie Tower, they are sending out this information about information sessions via email. They also have located a room for you, and that's all in the email blast that was sent out. So again, please if you're able to, come to the information sessions in those assigned rooms, wherein you'll be able to interact with other engineering disciplines too. Any other questions, concerns?
Okay, I did see one question on how to access the AFT software. So the link to be able to do so is on the presentation as shown right now. It's the flow.aft.com/UH. So if you go to that website, you'll be able to input information on yourself and your UH email address. So you do have to use your university email address to be able to receive the license. And the reason why it's set up that way is AFT has been very good to Fluor UH for this design challenge to be able to provide this at no cost. So they do want your UH email address.
So on the side, I have another question that's being asked. Do we have to register our team with Fluor or simply make sure we turn in our submission on time? We have a website, the conference website, which is shown here. Once you log in and register your team, you will be able to access all the narrative and design information, the past spreadsheet. So I would please register so you're able to download all the pertinent files. And then you are required, and then you can look at the critical date, wherein the submission starts sometime in October. I forget when that is. Thank you, David. It's your portal for the submission opens October 14th, but more important date to keep in mind is October 18th when the portal for submission closes. Does that answer your question, Mr. Severin? Or Ms. Severin? Okay. All right, good. Any other questions that I had? I'm trying to read another. So this part of the segment, all basic ideas are created based on Table 7. So our job as being part of the design is to manipulate pump locations and types of pipes to reduce cost. So that's the other question that we got from Severin. David, would you like to answer that? Are you able to see the question on the side?
I did not. I was not able to see that, but it was around.
Okay. So the question is, all the basic ideas are created based on Table 7. So the clarification they are asking for is, so our job as being part of the design is to manipulate pump locations and type of pipes to reduce cost. How would you answer that?
It is to identify the location of the pump station based on those two criteria for selection of pump. Now, the big driver of where that pump location will be won't necessarily just be from a hydraulic analysis, because you'll find several solutions that will work. However, the actual location location and excavation at that location and the associated costs with the equipment to be able to do so may not make it as cost efficient or cost effective. So you're looking at it from a hydraulics perspective of the cost of the pump that meets the criteria, and also the construction cost to build it at that site. What was also said was changing the pipe. For the original proposal that you'll submit, the 30-inch diameter pipe will stay the same. What will change is the wall thickness based on the pressures that will be identified from that pressure profile chart. The only part where diameters will change will be part of the ZBE, where you adjust it based on the flow rate, which you'll have to calculate the difference between 8 hours of operation versus the 24 hours.
Does that answer your question? Okay, moving on to the next question that was asked. Will these sessions be published for us to listen to again? Absolutely, which is why we are recording this session right now. Although it takes about 24 hours for me to be able to see this video and for me to be able to download it, the idea is for us to publish it on the conference website. Please get with Jennifer Knobloch. She'll be able to assist you with if you have any problems accessing it. Once we have the video published online, we will send a notification to everyone, an email, that the session has been posted. I think information session, which was the introductory session, has been made available already for the students to catch up. And this session, similarly, will also be posted. There'll be a lag. It won't be done right away. It'll be available in the next couple of days. Okay. We will send out a reminder to make sure that to give you instructions on where the video is posted. I believe Professor Chang is letting ME students, I think they have a link to the video archive. Okay. We will host it in a common repository so that all students have access to it. We'll let you know via email. Any other questions, concerns? Any, David, would you like to close this session with any comments? Ron, David? Okay, well, the next session will be tomorrow, again, same time, 4 to 5:30. I think room location has been sent out via email and WebEx information has been shared. And for tomorrow's session, Ron Mace, our subject matter expert in civil foundation design and excavation, will go over that section with you all. My recommendation is for all the students to review the narrative again one more time and be ready with any questions you have. That'll make for an efficient learning process. With that, David, Ron, would you like to add something?
I have nothing else to add. Again, if anyone has any questions, my email address, please feel free to send me any kind of questions. Thank you.
Yeah, this is Ron. I look forward to talking to you all tomorrow on the session on excavation and foundation design. So see you then.
Thank you, Ron. Thank you, David. And thank you, everyone, Professor Chang, Jennifer, and all the students who made the time to attend this session. Thank you for all those questions that you've asked that have helped better clarify this whole process. So good luck. Have a safe evening and a fun evening, and we'll catch you tomorrow. Bye.